So the next speaker is Dmitry Golovaty, who will speak on a topic which is different from what's listed in the program.
Which is kind of still the same topic, except that the title is written in a slightly different way. So this is a result of a joint work with Peter Sternberg and one former PhD student, Raghavendra Venkatraman, who is now at Carnegie Mellon, and Michael Novack, who is still at Indiana. The goal of my talk will be to describe a couple of toy models that we decided to analyze to understand what is going on in nematic liquid crystals with highly disparate elastic constants. So just one disclaimer that I'm going to state immediately is that those are toy models, so we hope that they do replicate what is going on in the real system, but I'm not going to make any claims that this is what I'm modeling here. And my talk actually is going to have, I guess, a strong relationship to the talk by Radu yesterday. All right, so let me first discuss a little bit, recall how we describe a nematic liquid crystal. So we already heard here about Assin-Frank and Landau-Dijon's theories. So in my case, I'm going to stick to the description that stems from Assin-Frank. So if we want to model a nematic liquid crystal which consists of material which consists of molecules with highly anisotropic shapes where you form ordered phases. The thing to do is first to devise a field which will describe the local state of a liquid crystal. In this case, it is a director formulation. So we describe a liquid crystal by unit vector field N, which is called a director. And then in order to produce an equilibrium configuration of a nematic in some domain omega, I'm going to stick to a variational description. So I would want to minimize some energy subject to certain boundary conditions or anchoring conditions as they are known in the theory of liquid crystals. One can consider additional effects, such as a field, for example. I'm not going to touch that at all. So a quick recap of the Assin-Frank model. So Assin-Frank model gives you an energy, elastic energy associated with variations of a director. It consists of three components. Now it has to be invariant in appropriate sense. So one can show that the second order model will have to have this form. Four components, each describes different type of deformations: play, twist, and bend. And there is a no Lagrangian saddle splay term, which is somewhat more difficult to describe. So my goal is to understand what is going to happen to minimizers of this energy when the elastic constant, typically people consider elastic constant to be equal, and in my case I want to understand what is going to happen when the elastic constants are very different. Just one comment here. We're going to work in R2 actually. So if two elastic constants K2 and K3 are the same, so that twist and bend terms are penalized in the same way, they both can be combined in a curl square. And so then we can always rewrite this energy just in terms of a gradient of n squared and a divergence of n squared. So n again has a unit length, so there is a constraint here. And we want to relax this by in the usual fashion, so by writing something similar to what you usually have for a Ginzburg-Landau model. except that gradient square and divergence square contribution are going to be penalized in a different way. And at the end of the day, I want to relax the constraint. So instead of a constraint, we're now penalizing for deviations of the magnitude of a director, in this case from 1. And so, as I said, we end up with a Ginzburg-Landau-type model, or in a sense, Allen-Kahn type model given the scaling here. Epsilon is going to be a small parameter. L is a coefficient of order 1. In a sense, one can think of this as a very particular choice of Erikson's model for nematics with variable of degree orientation. Okay, so I'm going to consider two possible cartoon problems, sort of. The first problem you can think of as a problem for a deep nematic regime, in which case the potential is constructed in such a way so that it's minimized by the magnitude of u being equal to 1. So then formally in the limit you would expect that the magnitude of u is 1, and then this term will remain, you will see in a second what we're going to get. So we're dealing with this variational problem. We're going to impose Dirichlet boundary conditions on a boundary of a domain omega, and I'm going to assume that u is in S1 on the boundary. So if we think about these models, so two limiting choices of this are actually well known. If L is equal to 0, it is already, as I already mentioned, it is a Ginzburg-Landau model. And if L is going to infinity, then you're going to get a Wheeler's-Giga problem that was already discussed last time, yesterday by Radu. And so in that sense, what I'm doing here is going to be some sort of an intermediate regime between Ginzburg-Landau and a Wheeler's-Giga. All right. So at the end of the day, we want to understand what sort of singular structures can form within this model and what happens when the elastic constants have a large disparity. So what sort of singularities one can observe here? So like it is typical for a Ginzburg-Landau type models, you would expect to see vortices. But in this case, because of the presence of the divergence squared term, you can easily convince yourself that now you have a difference between vortices like this of a hedgehog type and the vortices of where the director is parallel to the surface, so parallel to the boundary. For a hedgehog type defect, it's easy to see that the energy actually is going to explode as epsilon goes to 0. So this kind of vortices are going to be very expensive. On the other hand, the vortex, still a vortex of degree 1, so both on the previous page and on this page you see a vortex of degree 1, but this vortex is sort of amenable to divergence. Divergence here is equal to 0, so a vortex like that, in this case, is not going to contribute to the divergence term at all. So some vortices of degree 1 are going to be expensive and some vortices are going to be cheap. So we can have vortices. And also in this model, we can have walls because, again, there is a similarity to a Wheeler's-Giga. And you can understand it in a following way. So if we look at one-dimensional version of a model, so if, for example, I'm going to assume that I have a strip like this, the director points in one direction here, another direction here, and I'm going to assume that everything depends just on a vertical coordinate, which I think I called maybe y here. So if I want to minimize the one-dimensional version of my energy subject to these boundary conditions here, a couple of things are possible. Number one, it is possible that, in fact, nothing prevents a director from being just having a unit length. So I can drop the potential term. And so then you would just have a director winding from the bottom boundary to the top boundary, in which case you'll have a divergence contribution, and this term is going to, for large L, contribute possibly a large amount. Another way to connect bottom boundary to the top boundary is to actually get rid of U2 completely, say that U2 is equal to 0, and simply force a variation of U1. So U1, the length of U1 changes and comes back and direction changes and goes in the opposite direction. So if you assume that U2 is equal to 0, then you see that this term goes away. Everything is now written in terms of U1, and what you get is a standard Allen-Kahn type of energy. So when epsilon goes to 0, then you know that you're going to get some finite contribution, and that finite contribution is going to be independent of L. So then you would expect that when L is large, you are going to have essentially a wall that will form in the middle of a domain here. When L is small, then you would prefer just to wind from bottom boundary to the top boundary. Or if L is intermediate, then some combination of those might be possible. And that indeed is what is happening here. And by the way, just like in the Radu-Stock, the normal component of a director through the wall is going to be continuous. So that is something that we basically by a divergence theorem. So that is something that is going to be important in the remainder of my talk. So walls and vortices are two possible types of singularities that one can observe here. All right, so at the end of a day, I would want to send epsilon to 0. And I want to understand what sort of appropriate form of a limiting functional is going to be. I have to figure out the functional space. So in this case, because of a divergent square term, I would expect that for the limiting, for the limit of the minimizers of my regional functional, the divergent square is going to be bounded. So it is natural then to expect that the divergence must be NL2 for the limiting problem. So that means that we want the limiting functions to belong, the competitors in the limiting problem, we want them to belong to HDiv. And things must be S1 valued because of the penalty term. And once again, let me emphasize that I would expect that functions in HDiv are going to jump, they are allowed to jump with the normal component of the director being continuous across the jump, just like in this cartoon here. All right. Okay, so analysis of this problem is actually very similar to the analysis of Wheeler's Giga problem, and most of the results basically transfer with not a significant change. So for example, we have compactness. I'm not going to concentrate on this too much. And we also have, so I'm going to skip this. So because this is similar to Wheeler's Giga, then there is a large literature on that, and there are many people in this audience actually who work on that problem. So the limiting problem then can be stated as follows. As you probably would expect, there are a couple of contributions here. So one contribution is still contribution from divergence. So in the bulk, away from possible jump sets, you still retain the divergence squared contribution. And then also a contribution from the jump sets. The jump set can be in the interior of the boundary. By the way, U plus minus U minus is a standard notation. It's a jump in the quantity U across the boundary. And it is also possible to have a jump on the boundary of a domain. So we have these three contributions from jumps and from the bulk divergence. And then just as in the case of Wheeler's Giga, we can prove that a sequence of epsilon functionals, these toy epsilon functionals that we formulated, that they converge to that limiting functional that I just showed you. We, just like it is the case in Navilas Giga, again, not going into the details, it is sort of a type of a gamma convergence result because we have to assume that the limiting functional is BV, so that we have control over the jump set. Furthermore, we can, given that limiting functional, we can identify the Euler-Lagrange equation that the minimizer of the limiting functional must satisfy, and basically the Euler-Lagrange equation in the bulk, in this case, just says that the gradient of a divergence must be parallel to u, to the director. And on the jump sets, you can identify the jump condition on the divergence across the jump set. The interesting thing here, again, in a sense, similar to Navilas Giga, is that for an equation like that, equation like this can be written as a conservation law, but then using also a definition of a divergence, what actually happens is that the Euler-Lagrange problem for this limiting function actually is a couple of conservation laws that are supported on the same set of characteristics. So this is quite useful because then it allows us to reconstruct some solutions of the limiting problems you will see in a moment. By the way, so in this case, the second equation basically says that, by the way, I didn't mention that V is a divergence. So this is, theta is, if you write the director as a cosine theta, sine theta, then, so in the system of conservation laws, you have two unknowns, theta and V. V is a divergence. So the second equation basically says that along characteristics, the divergence in this case is not going to change, it's constant. And then the first equation, if you think about it, actually says that characteristics must be arcs of circles with a radius equal to 1 over the divergence. And in fact, so then if the divergence is equal to 0, then the characteristics become straight lines, and that is what you see for Navilas Giga. All right, so let me talk a bit about some sample problems here. So first of all, a quick discussion of a problem like this. So it's a problem in a strip. I'm going to think about a period of about infinite strip with a periodic solution. And such that the director is parallel to the boundary but in opposite directions on opposite edges of a strip. So that is a one-dimensional problem that I already showed you. In this case, it is possible to show that this one-dimensional problem is going to have a minimizer, and a minimizer is going to be, the structure of a minimizer is going to be dependent on a ratio between the elastic constant multiplying the divergence and the width of a strip. There is a magic value of 2 if L over H is less than 2. Then you will see a minimizer which has some divergence and some wall cost. And if L over H is greater than 2, then divergence cost disappears. So as you kind of would expect, for large L, the divergence is going to be 0 everywhere. And so all cost is going to be concentrated on the wall. If you simulate Lagrange equations for this setup, then indeed what you see in the strip is basically a one-dimensional wall, one-dimensional solution. For this particular simulation, I believe that the boundary data was, that the director was at an angle, at different angles on the top and the bottom. Again, similar to what Radu was talking about, actually, in this case, if L gets bigger, so if L gets bigger, divergence becomes more expensive. It actually turns out that these one-dimensional solutions become unstable, and you see these cross-tie walls. Next, what I want to discuss is the following. So I see a cross-tie wall. Now I know that I have my characteristic description of a solution. Would I be able to reconstruct these walls analytically, or maybe semi-analytically? So for that solution that I just showed you, this is a numerical graph of a divergence. And remember, I said the divergence must be of a level set for the divergence. I said that the divergence must be constant along the characteristics, so then level sets for the divergence must be characteristics. So these curves that you see here are kind of like characteristics of the limiting problem. And so then indeed we are able to reconstruct a solution using characteristics, as I'll show you in a second. And we discover an interesting point here. So the interesting thing that you can see is this, that you reconstruct a solution by using characteristics, you can compute its energy. And you can show that actually the energy of these characteristic solutions is going to be smaller than the energy of one-dimensional competitors. So that means that there is a range of values of the elastic constant that multiply the divergence over which the one-dimensional solution must be unstable. So how do you reconstruct a one-dimensional solution? From that previous picture, you see that you have several different regions in XY plane, 3 different types of characteristics. Sometimes characteristics connect different jump sets. Sometimes they connect corner with a boundary. And then there is a third region here where you have to figure out what the characteristics are doing, but you can do it, and you actually can reconstruct the solution. And so if you compare the quarter of the period here to the quarter of the period constructed by characteristics, you see that the behavior is basically very similar. And a similar picture if you want to draw level curves for the angle. Those are not characteristics, but again, the behavior in the quarter here is similar to the behavior that was analytically reconstructed. And actually, another interesting thing here is that if you make L even bigger, then you can show that actually the second sort of a bifurcation occurs, that you see cross-tie walls, which are or cross-tie wall type solutions, which do not look like a cross-wall type solutions that you see for lowercase l.
Sorry.
Yep.
I can't see the arrows. Could you just tell me which way they point?
So arrows here, down, down, up, and up.
And at the very top?
And at the very top, it's that. So it goes this way and that way.
Okay. All right.
Okay. And so once you plot all the energies, then you can actually discover that result that I already mentioned, that for a certain range of L's, you would expect that the one-dimensional solution has a higher energy than the cross-wall type solution. Right, and you can actually consider other, you can use characteristics to analyze even more complicated cases, but that's beyond the scope of my talk here. Okay, so second model problem. How much time do I have, Peter? Peter? 15?
You have till half past.
Okay. So then the second problem is I'm sort of kind of raising a temperature now so that I allow for coexistence of the cartoon now is that allow for coexistence of a nematic and isotropic phase, which means that I basically keep the very similar structure of my functional, except that now I'm going to consider a potential which is minimized. This is a Chern-Simons-Higgs type of a potential, which is minimized by the magnitude of u by length of u1 and length of u being 0. So that means that I'm allowing now for a coexistence of an isotropic phase and a nematic phase. Otherwise, the setup is exactly the same as before. So again, in the same way, I'm still interested to understand the singularities that will form in this case. Clearly, you can have more singularities now than before, because now I allowed for coexistence of 2 different phases, so that means that I allow for interfaces also, for interfaces between nematic and isotropic. And I also want to understand the influence of large disparity between the elastic constants on the form of the solutions, in particular the form of the interfaces that we're going to see. And motivation for this from actual pneumatics, from experiments with actual pneumatics. This is a picture, this is actually an experimental picture from Oleg Lavrentovich. So this is, this depicts things that are known as tactoids, nothing special about tactoids in this case, except that those are inclusions of isotropic phase inside the pneumatic phase. And you can see that two types of things, in particular, two types of things are possible. When you see that the director is parallel to the boundary, then the tactoid has a round shape. When director is, so in this case, this is +1 degree defect, this is a degree 0 defect. The tactoid like that, as you can see here, has singularities on the boundary, has a singular shape. In both cases, though, the director is parallel to the boundary. One thing that I should note here, that it looks like these are arrows, but actually they're not arrows. I think they're just straight lines, but measured at circles. So this is just a comment. So that means that somehow we have to understand why, if we think that things like Osin-Frank, relaxed Osin-Frank model, or possibly Landau-Digen's model that reproduce correctly what happens during the transition, then you want to understand why the singularities form and why the director must be parallel to the boundary. All right. So I'm going to consider two different cases. One case will end up being rather boring, and that case is when L is not a constant, but I allow L to depend on epsilon, I allow L to go to 0 along with epsilon. So that means that the disparity is sort of weak. It's still quite strong because L epsilon is much bigger than epsilon, but both go to 0. In this case, the result is, it can be shown that this energy actually gamma converges to just a perimeter. So because it converges to a perimeter, that means that in the limit, I don't expect that the director is going to be coupled in any way to the interface. So I cannot expect that the director is parallel to the interface. So that means that for this to happen, I should expect some sort of larger disparity. And that indeed what happens if you assume now, again, that L is a fixed parameter of order 1 and epsilon goes to 0. So in this case, the proposed version of a limiting functional is as follows. Basically, it is still that the divergence square term will be retained in the limit as epsilon goes to 0. We can still have walls. So this is the same kind of a wall term as what I showed you before, the wall cost. But now also we have a cost which is associated with the interface. In fact, this cost and that cost, in a sense, are very similar because there is really no big difference between an interface and a wall, except for the fact that for an interface, because we have to connect an isotropic phase to a pneumatic phase, and you expect that the normal component of a director must be continuous across the interface, then that means that the director must be parallel to the boundary, parallel to the interface. But on just regular jump sets, it does not have to be parallel. It might come at some angle. All right. And so, just like before, you would hope that some sort of a gamma convergence result would hold. But it turns out that for the potential that we're considering here, the existing techniques or modification of the existing techniques, for example, Ginzburg results, and I anything else. So Radus results are not really going to describe what is going to happen. So we can determine an upper bound result, but we cannot do anything with the lower bound. But we do make a conjecture that there is a gamma convergence here. So the principal difficulty, again, per Radus talk, is that you don't know a priori that you do not develop a microstructure on the boundary. So eliminating that possibility, so far we don't know how to do it. Right, just summarizing here the results that we have at this point. So the thing to keep in mind for now is that for the interface, the director is always going to be parallel to the interface. And I'm going to finish my talk with discussing several examples, just like I showed you before for the case of a Ginzburg-Landau. So first, again, if I look at the setting similar to this, basically it's a strip with the director pointing in the opposite directions on the top and the bottom boundary. You numerically solve this, and you see the behavior, which is exactly the same as what you already have seen for the Ginzburg-Landau potential case. If L is relatively small, then you see that the director turns a little bit, then jumps, and then it continues turning. So in this case, it makes sense to have both bulk divergence contribution and some sort of a wall contribution. Then as you crank up L, in fact, not by a very large amount, what you see is that now the divergence contribution is completely gone, and all cost is just going to be concentrated on the wall. The interesting thing, which we do not really have an explanation for yet, is that for the Ginzburg-Landau case, as you keep increasing L, then this solution becomes unstable and you see cross ties. In this case, you don't see anything like that. So you can raise L as much as you want, and numerically at least, you are not able to see any symmetry breaking. So you just see a one-dimensional solution. We think that it might be associated with the fact that now 0 is the minimum of your potential, so you depart 0 at some very slow rate, so maybe that is the reason. Well, this is not very interesting, it's just the wall profiles here. A more interesting problem is a problem in a disk, where we are going to assume here that the solution basically looks like e to the I and theta on the boundary. So on the boundary of a disk, I will request that the director winds k times as I go around the boundary. And I want to see what sort of energy minimizer I'm going to observe. And this is what we get for a vortex of degree -1. You see that so the blank part of the picture is an isotropic phase, nematic phase. So you see that both are separated by an interface. Director is parallel to the interface. Red things are basically walls. And an interesting point here is that if this was just a regular phase transition, you would expect that proceeds by curvature motion, you would expect that the interface will just shrink to a point and disappear. But those are stationary solutions. So in this case, somehow the competition between elasticity and the perimeter reaches some sort of a happy equilibrium, so that you get some surviving isotropic phase, at least within this description. As you make L smaller, the size of this island gets smaller. If you make it bigger, the size gets bigger, and eventually it touches a boundary. If you increase the degree, so from -2 and -3, you basically see a very similar picture, but now you get more corners. if you go back to degree 2, so now the standard Ginzburg-Landau result is that vortices, one vortex of degree 2 is more expensive than two vortices of degree 1. In this case, actually, it kind of is the same story. By using different initial conditions, you can either get one vortex of degree -2 or two vortices of degree -1. Vortices of degree -1 are going to be less expensive, although this degree -2 vortex seems to be at least numerically stable. It does not fall apart into these two. If you use a boundary data of degree +2, then remember that vortices of degree +1, the tangential vortices, divergence, loving vortices, are allowed. In this case, degree 1 vortex is just a standard degree 1 vortex that you would expect, for example, in the Ginzburg-Landau case. So you start with a relatively small L with one degree 1 vortex at the center. It falls apart into two vortices of degree +1. But then something interesting happens as you make L bigger. As you make L bigger, you make a divergence more expensive. If you make divergence more expensive, variations of a director in the interior are more and more costly, and you see that actually the solution tends to a constant equal to E1, the unit vector in the direction of x-axis, and all action now is concentrated on the boundary, and basically this yellow curve along the boundary, I'm not sure if you can see it or not, but you have a wall, the wall along the boundary. And in this case, we also decided actually to check our conjecture that the wall cost in this case must be one-dimensional. This is sort of an extreme case. It's not a one-dimensional, originally one-dimensional solution, right? You just have some random wall that form. So you can check if the wall can be one-dimensional, so we can compare the profile of a heteroclinic solution which connects the appropriate orientations of a director with a cross-section of the wall, and you see that two things, so this is heteroclinics and the actual profile across the wall, numerically computed wall, they are exactly the same. So the conjecture that the wall must be one-dimensional is kind of supported by this observation. One other interesting thing here is that if you let L go to infinity formally, then you end up with some kind of an analog of Avila's giga functional, except that now this is an Avila's giga which can have both interfaces and walls again. So that is a functional which will have two perimeter contributions and divergence otherwise equal to 0 in the bulk. And in this case, as I mentioned, characteristics are going to be straight, and that degree -1 vortex that I showed you before actually can be computed explicitly, analytically, and it turns out that degree -1 vortex interface corresponding to degree -1 vortex actually must satisfy this equation. And on this picture, I'm showing both the solution of this equation and the numerics for L large, and you see that the match actually is pretty good. And so the last thing, what about the shape of tactoids? So this is a simulation for the epsilon level functional, gradient for the gradient flow for the epsilon level functional. So at the infinity, in the infinite domain, so this is a large domain which intends to model a situation where you're infinite, in R2 basically, with the director being constant at infinity and parallel to a unit vector along x-axis. So here, if you create an interface, the degree of the vector field around the interface must be 0, because degree is 0 at infinity. Then nothing actually holds silent. It will just shrink to 0 because there is no topological reason for this island to exist. So the picture that I'm showing here is actually transient. And so what you see again is a nematic island with singularities, with interface which has two singularities and walls that go to infinity. So let me just mention this. So then in this case, if you assume that L is very large, in one of the previous slides you saw that L equal to infinity and L relatively large give you more or less the same picture. So we can try to reconstruct this nematic factoid by using our characteristic solution, and you can actually do that by some careful manipulation. You just have to solve one ODE, and that ODE has to describe the shape of the interface and the shape of the wall. You construct the ODE, you solve it, and you see that you get two solutions. You have to impose area constraint in this case, because by itself the isotropic tactoid is going to shrink to 0, but you see a very good match between the two. All right, that's what I was going to say. Yeah.
Other questions? Yeah.
I might have missed it, but is there something with the role of surface tension for the tactoid here?
So the surface tension actually is something that comes up from the original functional, right? So that perimeter contribution that you get has some cost associated with orientation of a director on the wall or on the interface. So the surface energy actually comes from the bulk energy of the epsilon problem in the course of a limiting process, right? Because in the beginning, it's the problem is diffused. It doesn't know if it is in phase 1 or phase 2. But as this coefficient epsilon goes to 0, right, then you split, your solution tends to a state where you're isotropic in one part, nematic in another part, and then the cost of a jump is something that comes out from the limiting procedure. So you don't need to somehow devise or postulate it from the beginning.
Okay, there's no added ingredient needed.
No. It just all comes from the original Ginzburg-Landau-type formulation.
Any other questions? Yes.
So in the first model, for the hedgehog boundary condition, so you fix L and you let epsilon goes to 0. So what's the shape that will appear?
For a hedgehog like this,
Yeah, on a disk.
it will just rotate, right, and become a.
So you didn't have a picture.
I didn't have a picture, but you can actually show that the only possible choice actually is.
Right, because there is a frustration between being a curl and
being a div. But so you become a div as you radially collapse towards the center.
there is a wall forming at the boundary, or
No, I don't remember. I don't think so. I think it just smoothly.
up to the center, like this.
Yeah. So it's like if you go along the radius, it's like that.
Okay.
Any more questions? Yes.
So in the circle where your boundary data is giving you a certain type of defect, you normally expect your central defects to split into half defects.
Yeah, that's what I was saying. That in
So is that not allowed because your n is oriented here?
it is allowed, right? So remember, in this case, let me go back to this picture. Here, for instance. So this is a defect of degree -2 and two defects of degree -1.
But normally,
Normally, you would expect, yes, you would expect that it will split, but in this case, no, it just sits there. So you have to start from some other specially designed initial conditions to get here. And again, it's not clear if it is because the potential somehow is very shallow at 0 or what is it. Because typically that would correspond, 0 will correspond to a maximum, not to a minimum, right? So.
comparison with experiment is not so easy, right?
No.
Because K3 can be made as small as you want, but
Yeah.
your division doesn't.
Yeah. Yeah. Well, in some sense, for example, you can make K2. Right. There is some symmetry between curl and div. So if you can show this for divergence, you can do the same thing for the curl. Right. So you can penalize curl more heavily, and then the picture will just flip.
But experimental is bad.
But- Yeah.
Very good. So we'll break for coffee and reconvene at 11. Let's thank Dmitry again.